So last time we were talking about matrix transformations. And let's just quickly go back what we were talking about. You have a transformation, we're going to call it t, and t of x is like a function. You plug in an x, it outputs t of x. But now x is a vector, and the output t of x is also a vector, and they might be different sizes, they might be the same size. And we have what's called the range. Let's start with domain and codomain. The domain is everything that gets inputted, or that can be inputted into the function. The codomain is what space the outputs get mapped to. And the range is what actually gets mapped, the actual y value, not the y values, the actual outputs to the vectors. Yeah. Yeah, that's what we started the next thing with, right? So x is some vector in the domain. The function t, the transformation t, maps that, or changes that vector into another vector called t of x. We call that the image. That's the image of x under this transformation, and that guy lies in the range. It also lies in the codomain. Okay. And we are interested in these transformations that end up being just matrix multiplications. So if we can multiply a matrix to do the transformation, to evaluate the function per se, then that's what we call a matrix transformation. So we have this definition T. It takes R2 vectors and turns them into R3 vectors. And this definition here tells you how that happens. It tells you what you actually calculate to make that happen. And we figured out that if you just use this matrix and multiply that, your vector, that will do the exact same thing as this. Okay? So we asked some questions like, what are the domain and codomain of T? The domain is R2 because if A is 3 by 2, let's do it down here. A is 3 by 2, then the vector that we multiply by has to be 2 by 1, right? So the vectors that we plug into the transformation have to be R2 vectors. And what gets outputted is 3 by 1. So the codomain is R3. There are R3 vectors that get outputted. The actual range ends up being the span of these two columns of A. If you span those column vectors, you get all linear combinations of those columns of A. That ends up being a plane, right, in R3. So we have an R2 vector, U. It has to find T of U. So that's the image of U under the transformation T. So all you have to do is multiply A times U. So A was 1, 3, negative 1. Negative 1, 0, 2. So if we multiply A times U, we'll get T of U. We'll get the vector that gets outputted, right? And we did this last time, right? So let me see what we get again, see if we get the same answer. So it's got to be an R3 vector. I'm going to use the dot product method. So I have negative 1, negative 5, negative 3, 0, 1, and 10. Is that what we got last time? Okay, so that is T of U. Right? Yes?
So that's the same thing if we use the x1 minus x2.
Yes. So what would be x1 minus x2? be -1 minus 5, that's -6, right? What's the next one?
3x1.
3x1. So 3 times -1 be -3.
And then negative x1 plus 2x.
So that is
1.
-1, -1 is 1, and then 2x2 is 10. So that gives you 11.
So
Yep.
we have to find out the A matrix.
Yes. Yep, you'll have to find the A matrix. Yep. You know, there'll be a question that says find the transformation matrix, find the standard matrix for the transformation. Yes.
So the codomain is the output, so to speak?
So codomain is what type of vectors come out.
Right.
These are R3 vectors. That's the codomain.
So, okay,
The range is what actually gets outputted.
okay, so that answers the range.
The range would be all possible A times X's,
I see.
right? So all possible A times X's would be x1 times this vector plus x2 times this vector, right? We plug in anything we want for x1 and x2, and that'll give us one of those, right? And that is the span of those two vectors. And that ends up being a plane, right, in R2. A two-dimensional plane in R3, because they're R3 vectors. Yeah.
So we can make it into R4 by using another, like, x2 minus x1.
Yeah. Yep. You could come up with whatever you wanted. Yep. You could come up with a million size vector, you know, 1,000,000 by 1 vector. So the next one says determine if this vector is in the range of t. So let's call this v. So v is in R3, right? It's in the codomain. It's a three-dimensional vector. But is there an x in R2 such that AX equals V? Right? That's the question. Is there some vector that we can multiply A by and get V? If that X exists, then yes, that V is in the range. I know it's in the codomain because it's an R3 vector. But is it in that plane, right? So the way to figure that out is to solve that equation, AX equals V. So augment A with V. I forget A. 1, 3, -1. 0, 2. Is that right? Augment with the new, or augment with V, write the output, and see if there's an X. I'm hoping that it saved this. No, it doesn't like it did. So I'm going to row reduce this in the calculator. So I don't know why I have an extra column in here.
You picked A, and it was a 3 by
Okay, let me go back and look at A. That's not A. I must have. Look at B. I don't know what happened. Let's do it again. I'm sure the video will show my mistake. I'll figure it out later, but that's another bad thing about these videos, that it documents everything I mess up. All right, so we get that. Okay. So remember, it's augmented here, which means this statement here says no solution. Right, so the answer is no. You cannot find an R2 vector that you can multiply by A and get this vector V. So it's not in the range, even though it is in the codomain, right? It doesn't lie on that plane. So the next question says, find an x in R2 whose image under T is this vector. So it's almost asking the same question, right? So if we call this V, it says find an x in R2 whose image under T is this. So looking for the x in R2. Such that A times x equals V. So it's not just, is it in the range? We're wanting to know exactly which x in the domain will map this, will map to this vector, right? So I'm going to do the same thing. I'm going to augment V with the columns of A. And we get this. It's augmented here. So do we know the x, the vector x? So it has to be 5 for x1 and negative 3 for x2, right? So if we multiply A times this x, we will get that V. So this means a lot of things, right? So it also means that this vector v is in the range of the transformation. It means that this vector can be written as a linear combination of the columns of A. It means that it's in the span of the columns of A. It means it's in the plane that's spanned by the columns of A. Yes?
Are these not all synonymous? Like, could you have one but not the other?
No. They're all the same. Those are all the
those
same.
Are like different terminology they'll ask us about the same.
Yes. Yep. It's going to be like that all semester. Okay? We're going to have a running list of things. It gets to like M and N. They all mean the same thing. Okay? So,
Why did you do that? That's so nice.
I didn't do it.
know,
I didn't write the book.
But like, why? It just seems...
Because all those different things are useful in different areas.
Okay.
But it all comes back to the same thing. But is X unique? Is there any other X that will work? When we solved this system, did we get infinitely many solutions or just one? We just got one. So that means it's unique. If you got a free variable and you had infinitely many solutions and it's not unique, you can come up with different X's that'll make it work. Here, there's only one way to do it. So the answer is yes. We have one solution, it's unique. There's only three options: no solution, infinitely many, and one solution which makes it unique. There's only one of them. All right. So we have a new matrix, and this A times X is going to be our transformation T. So T is A times X, and this is the A. And we want to know what are the domain and codomain of T. So what kind of vectors can you plug in, and what kind of vectors come out? So you can tell by the size of A. It'll tell you what kind. So what's the size of A? 2 by 3, right? It's got 2 rows and 3 columns. And if we multiply by an X, right, that's how we do the transformation. What size does it have to be? It has to be 3 by 1, right? So these have to be the same. And this is what kind of vectors pop out. This is the output. Be 2 by 1. So the inputs are vectors in R3. The outputs are vectors in R2. That means the domain is R3. And the codomain is R2. Yes?
Can you give it like a 3 by 2?
No. Sets. Or you have to write out all 3 by 1 real vectors. You can write that. That's what this means. This R3 means all 3 by 1 real vectors, real entry vectors. So given this U, which is a R3 vector, right? So that's our input. Find T of U, the output, the image. So we just multiply A times U. What size will the output be? R2. So I'll have 2 entries, and I'm going to do the dot product method for multiplying these together. So for the first entry, I'm going to take the first row of A and this column in X and dot product. I multiply the corresponding entries. So 5 plus 6 plus 7. 5 plus 6 plus 7. $18? Five plus 6 is 11, plus 7 is 18. Then the second entry, I've got to take the second row of A, dot product with X. So this is 15 minus 3 minus 7. 5?
Can we do this on a calculator?
Yeah.
I mean, not that, but like, get two different matrices and multiply them together.
Okay. It's a lot of work. It's a lot of work in the calculator, though. It's a lot quicker. I would use a calculator if I had big matrices I have to multiply. But, later on we're going to multiply, a 3 by 2 matrix times a 2 by 2 matrix or 2 by 7 matrix, okay? And we might make you show all that just so you know how to do it. But we're going to use the same method. We're just going to keep going. Okay. So this guy is T of U. That's the output. Okay, that's the image of U under T, is what we say. It's the image of U under T. Yes?
So for the dot product, did you just multiply by the 3 on the second part, or did you use the -1?
So this entry is 3 times 5 plus -1 times 3 plus 7 times -1. So 5 times 3, that's 15. 3 times 1 is -3. And then 7 times 1 is -7. That's how I got 5. Anybody else? Questions? All right, find an x in R3 whose image under T is this, 7, -14. This is some vector. We call it V. Find an x such that A times x equals V, right? Because that's the transformation. A times x is T of U, or T of V. No, T of x, right? This is T of x. That's the image. Can we find an x that will make V the image of x? So we're going to augment. So what is it? 1, 3, 2, -1. And -7, 7. Okay. I'm going to use the calculator here. What size is this one? 2 by 4. Do I get this? Does this system have a solution? It has infinitely many solutions. Do I have a free variable? Yes. So this, remember the inputs are in R3. So I have an x1, x2, x3 I have to solve for, right? So say x1 is negative x3 minus 3. x2 is 4x3 plus 5. And x3 is whatever we want it to be. It's free. It says find an x. So all we have to do is come up with one solution out of this. So we can let x3 be 0, and that would give us negative 3, 5, 0. Right, would be one of the solutions.
Does that mean you can put anything for the?
It's free. Yep. X3 is free. You can plug in anything and you'll get a solution. Now sometimes we might say non-trivial, which would limit you. You can't have the 0 vector as a solution.
Or would this count as a 0 vector?
No, it's not a 0 vector. We're only worried about trivial if the system's homogeneous. If that right side is 0, that's the only time we're worried about if it's trivial or not. So there's one example. So this is when x3 equals 0. Right. Is this unique? No. So next it says determine if this vector 9, 8 is in the range of t. Well, if we were to augment this vector instead of the one previous, the left side would row reduce exactly the same way, and these parts we wouldn't know. The left side of the matrix would row reduce the exact same way. So can this have a no solution? No. That means this vector is in the range of t. In fact, every R2 vector is in the range of this t. Yeah.
Okay, so when we get our A vector, why don't we just get the row reduced form?
That is the row reduced form.
Well, that is, but like the original, since if it doesn't change no matter what we augment it, is it because when we multiply it, it changes the output?
So when you're row reducing,
Yeah.
you're changing these by the column, right? These will change based on what you plug in here.
Right.
These will change. These will not, because all these are the same. This is the same here as this one.
So when we find the A vector, we might as well just find the row reduced form of that vector.
Talk about the A matrix.
Yeah.
When you find A, and we've already row reduced it once. I don't need to do it again. I've got to do it at least one time. And I went ahead and augmented with this and found a solution because I was asked to do that. And this one, I know I don't have to do that again because I know that I'm going to get a solution. The answer does not say find the solution. The question does not ask me to find x. If it did, then I'd have to figure out what these two are. Right.
So what about, does that mean there's no two-dimensional vector that won't be a solution?
Right. That's exactly what it means. Yep.
So everything's a solution.
Yep. Remember, the range is the span of the columns of A, right? Well, if I just span these two columns, they're independent, right? So just those two span the entire R2 space. You could get every vector just with those two vectors.
What about when we wanted to augment with 4 and -2? Since that could be written as a linear combination of the others.
It would work.
So you don't need those.
So these three vectors, these three are not independent because I can write the third one in terms of the first two. But I know the first two are independent, and I have two of them in R2, means if I span them, I get R2. I get all of R2.
So you need at least a number of rows to be independent in the matrix.
Yep. So for R2, I need two independent R2 vectors. For R3, I need three independent R3 vectors. Yep. So this is a case where the range and the codomain are the same. Okay. We call these transformations or functions that are like that, we call them onto. That's when the range and the codomain are the same. You don't have to know that. You will for another class, not this one. Okay. Very important concept here is the transformation what we call a linear transformation. So these transformations are like functions. Do they have this property that we call linearity? Are they a linear transformation? And they are if they satisfy two conditions. So the first is if you take the transformation of a sum of vectors, it's the same as taking the sum of the transformations of the vectors separately. So can I add the vectors first and then do one transformation? Or can I take two separate transformations of each vector and add them together? Do I get the same thing? If that's yes, then that satisfies one condition. Yep.
So multiplying x1 by x2 and then adding 3 wouldn't be a linear transformation.
Say it again.
So multiplying like x1 by x2 and then adding 3 as one of
We can check that.
Because you can't just have the one argument, right?
If we add x1 and x2, then what multiply? x1 and x2? Is that what you said?
Like, so u and v and t, they're not different arguments, right?
U and v can be the same or different.
They're like two different things you're plugging into the matrix.
Two different vectors.
Two different vectors, independent of each other.
They don't have to be independent. In fact, it says for every u and v, so independent or not. Okay. The second condition is, can you factor a scalar multiplication out of the transformation? So is taking the scalar multiple of a vector and then transforming it the same as transforming the vector and then taking the scalar multiple of that vector? Is all that the same? Then if you satisfy both of those conditions, it's called a linear transformation. You already know some things that behave this way. What about derivatives? When you have a sum of different terms and you take the derivative of that, can you just take the derivative of each piece separately and add them all together? Can you do that? Can you?
Is it separated by plus and minus?
That's how you do it, right?
Yeah.
If I'm finding the derivative of x squared over 3 plus 3x plus sine, right? What do? You take the derivative of each one of these and add them together, right? So this is, you would take the derivative of this plus the derivative of this plus the derivative of this. Right? What is that? 2/3 x plus 3 plus cosine. Hey, I can do calculus. Okay, right? So that's taking, that's doing each derivative separately and adding them together is the same as taking the sum of all these first and taking the derivative of it. Okay. In fact, it's so hard to do it this way, we never do it that way, right? We have to break it down to be able to do this, okay, without having to use the limits definition, right? And then, can you factor out constants when you take derivatives? Yeah. So here, I could have factored out this 3, called it 3 derivative of x, right? So derivatives have this linearity property to them. What about integrals? You take integrals separately in a sum. Can you factor out constants? Yes. All right, so this is a nice property to have, and we are interested in these transformation of vectors that have the same properties. Okay, so we call it, if it has these two properties, it's called a linear transformation. And it says, note that if t of 0 is 0, if t is linear, so it has to be 0. If you take the transformation of 0, you get 0.
So you can't have a plus 1 or anything. Transformation.
Right. If you take the transformation of the 0 vector, you have to get the 0 vector in order for it to be linear. Okay. So my eraser is slow. Come on. There we go. All right. Well, let T be a transformation that maps R2 vectors to R2 vectors. It's going to be linear. Let it be a linear transformation. It sends the vector u to 9, 5, or sorry, the vector u 9, 5 into negative 1, 2. It maps the vector v negative 1, 4 into 3, 8. Use the properties of a linear transformation to calculate these 3 different transformations. So let's do the first one, t of 4 times u. Well, since we know that t is linear, we can factor out this scalar. Right? Remember, I can't write in bold, so I have to put in the vector symbols. Sometimes I forget. And I know what t of u is. What is t of u? Negative 1, 2. It tells us that it maps u to this vector, so that's t of u right there. So this is 4 times negative 1, 2. B is t of negative 2 times v. So we could say negative 2 t of v. And what's t of v? 3, 8. So that is negative 6, negative 16. So for C, t of 4u minus 2v, that's the same as t of 4u plus t of negative 2v, which we just calculated already. So you just need to add those together. I was going to open the blinds, but the rod is broken off, so we're stuck. So add those two together. It's like negative 10 and negative 8. Is that correct? Yep. Sorry?
Why do we add them instead of subtract?
I'm adding the negative. Just because I've already figured out this one, right? So just makes sense to just add these two. If I didn't have negative 2v already, then you could subtract 2 times v. It'd be the same. It'd be the same thing. Okay. So here's the hard part. We have a definition of a transformation. We want to determine if they're linear or not. And if we have to show that they are linear, we have to show that they satisfy those two conditions, right? For every u and v in the domain of T. And that's the hard part. We have to prove it for all. Okay? Now, if we figure out that it's not linear, then all we have to do is come up with one example where it's not true. Does that make sense? So, if it's not true for all, that means there's at least one where it's not true. So we just have to find one example. It's called a counterexample. So the opposite of all is at least the opposite of none is at least one, right? So if we want to prove that it fails, we just need to find one example where it fails. If we want to prove that it's true, we got to prove it's true for all. Okay. So this transformation is, it takes R3 vectors, right, and it sends them to R2 vectors. Does everybody see that? So the input has 3 entries, and the output only has 2 entries. So what we have to show is for any 2 vectors that we could pick in R3, that we can satisfy those 2 properties. So let's pick 2 vectors. They have to be able to represent every vector in R3, right? So we'll just say, let U be this one, right? And V be this one. So U1, U2, and U3 are the entries of U, and V1, V2, and V3 are the entries of V. And they could literally be any 2 vectors in R3, right? So if we show it's true for these, then it's true for all. Because we can plug in anything we want there, right, to make it work. So let's take the transformation of u plus v and see if it's the same as the transformation of u plus the transformation of v. Okay, that's our goal. So transformation of u plus v. So what does that look like? It's an R2 vector, and the first entry is the difference between these two, right? So u plus v, let's do this to the side maybe. u1 plus v1, right? u2 plus v2, and u3 plus v3. That's how you would add u and v. So if I transform that one using this definition, I'll subtract the first two entries. So it'll be u1 plus v1 minus u2 plus v2. Just subtract the first entry and the second entry. And then the third entry, I'm going to multiply by 5. Need to make some room here. I don't have enough room in this thing, so I'll have to make some room. So let's just simplify a little bit. So let's say this is u1 minus u2 plus v1 minus v2. Is that the same thing? I just kind of rearranged it, right? And this is 5u3 plus 5v3, right? Is that the same thing? Okay. Well, that's the same as this vector plus this vector. You agree with that? If I add those two together, I get the one previous. It's kind of decomposed it right into two different vectors. So what is this first guy? What's that? What's this first term here? What is u1 minus u2, 5u3? What is that? Look at the definition of t. It's the transformation of u, right? If we plug just u in to t, this is what comes out. Yes? You can. What about this second one? It's transformation of v. So this is t of u plus t of v. So that's the first condition. We just proved it. You can literally plug in any u and v and it'll work because I just showed that it will work no matter what the u and v are. So that's condition 1. I'm going to have to forget this one for a second. We need to prove condition 2. Scalar multiple. Can we factor out a scalar multiple? So let's find the transformation of any scalar c times this vector u that could be any vector in R3. And we just need to remind ourselves, what is CU? That would be, you multiply the scalar times each entry, right? That's how you multiply a scalar. So if I transform this one, I get the first entry minus the second one, and 5 times the third one. Right? So this is the same as this. Do you agree that's the same? That's C times this guy. U1 minus U2 and 5U3, which is C times the transformation of U. So that means that that one is linear. That one's a linear transformation. So why would we want to check to see if it's linear? First of all, the properties are nice to have. Second, if it's linear, then you can always write a matrix transformation for the transformation. You can always find a standard matrix for the transformation. All linear transformations have a standard matrix. Okay. What about the second one?
The 5 come from up there again?
Which 5?
What is that?
The 5 is in the definition of the transformation.
The problems are like 2 is 1.
Are my notes not lined up?
No.
They're not on this one? Okay. Sorry.
They're on the same page. They're just flip-flop.
They're flip-flopped. Okay. Sorry. Okay. Sorry about that. So let's look at this other one. Four x2, 3x3.
Can we just say no because being a zero vector does not a zero vector?
Yeah, that's good enough. Let's find another one though, just to show that one of the other ones fails. So what about if I take this vector plus this vector, and I get 8, 2, and 7, right? So we'll call this our U and V, right? So what about the transformation of U plus V? It's 4x2, so 4 times 2 would be 8. And the second one has to be 3, and the third one is itself. So that's transformation of U plus V. What about the transformation of U and the transformation of V? What happens when you add them? So transformation of u, 4 times x2, and then 3, and then x3, and then v, 4 times x2, be negative 8, and then 3, and then 1. What happens when you add those together? Get the 6 instead of the 3.
Does
Right.
it also fail the other test?
Yes, it will fail the other one too.
And we could also just use the letters, just like,
You could, yeah, you could do the same with the letters. Yep. But you can see, you know, I just picked an example and it failed. That's all you have to do. You have to find a counterexample. If you want to show that it's true, though, you have to use the letter. You have to use the generic vectors.
so if you can't tell by looking at it that it's going to fail, then just go with the letters. So if it's
I would go
right-
with the letters, yep.
So you just picked numbers.
I just picked any two vectors, and it failed.
I was about to ask you, what made you determine those numbers? But no.
I didn't. They just popped into my brain. I knew it was going to fail no matter what. So these are not equal, right? So it's not linear. Yeah.
Should that 3 equal 2 when it's u plus 1? So, I mean, t equals
What was this supposed to be?
This one,
b. Yeah.
that 3, it's you take this vector and apply the transformation. So you take 4 times x2, so that's 4 times 2, it gives me 8. The second entry has to be 3, and the third one is whatever this third one is, right? So it has to be the 3 because the way the transformation is written. And that's the problem with that one, is that constant in there.
What if it was a, if all 3 of them just return numbers? Then that would fail the 0, right?
They were all constants.
They're
Yeah.
all constants. But what if all the constants were 0? So no matter what, it returns a 0, right?
It will fail both conditions if they're just constants in there. Yes.
Means the constants are just 0.
I think if they're all 0, it might pass. I think it might pass if it's just the 0 vector.
So that would still count as a linearly.
Uh, If the definition says 0 out the vector, I think it will count. Yes.
So, and just because it passes one test doesn't necessarily mean it'll pass the other.
Right.
You have to do
You have to do both. Yes. There is a way to do them both at the same time, though. You can do them both at the same time if you just check this condition. That counts for both. So you can check that one. If that one passes, then it's linear. But sometimes it's easier just to do one at a time. All right.